Hello everyone, I am Sushil Kumar, a BTech third year student at IIT Mandi, and today we are going to simulate a problem, the flow past diamond for 2D case. So this is our geometry, a rectangular geometry we are taking of width 15 meter by 10 meter, and here is the obstacle like diamond. So we have taken a shape like diamond. You can take any kind like circular or square or whatever. So this is the obstacle we are taking, and our flow will start from here and will leave the geometry from this side. So we have governing differential equation. So as we are considering the 2D flow, so the velocity in third direction, that is we consider in generally omega is equal to 0, and the here in continuity here comes the time varying density. So we are also considering the our flow is incompressible, so density is not varying with time, and in this is our x momentum equation. So for 2D case, so in 2D we are also neglecting the gravity. We are not considering the gravity in x direction, and we are also not considering the gravity in y direction. So there are some assumptions. So first of all, the no slip on the walls. So wall has zero velocity. At wall the fluid have the velocity 0. Incompressible fluid, so velocity is not density is not changing with time, or density is constant throughout the throughout our geometry. And 2D transient flow, gravity free surface, and initially we are taking a velocity is equal to 1 meter, that is our inlet velocity, and this is our outlet. So we will changing the inlet velocity for different Reynolds number, and we will see how they affect the different parameters. So this is our simulation setup geometry. So first of all we will create a geometry in Workbench 18, and then we will create mesh, and after creating mesh we will go for solver. So we have different solvers in OpenFOAM. So after we creating geometry and mesh, we will solve the problem using OpenFOAM software. So we will select a solver. We will select a solver, and then we will edit tutorial case. So we have different things there to have to edit, like boundary condition and all. Adding geometry to the case file, see results in Paraview software. So these things we will see later. So let's start with geometry. So this is the Ansys Workbench 2018 we are using. So we'll start from here, new component system, and we'll go in mesh, double click on geometry, it will take a while. So we'll take YZ plane, look at sketching. So our outer boundary is like rectangular, so we'll create a rectangle, and for simplicity we will make a circle to make diamond. Circle. Make dimensions. So our V2 D5, that is 1 meter. H is 15, L3 that is 5 meter, L what is 2, 5. Then D5 and it is 1. Now we'll make diamond here, so draw line. Dimensions. Make them equal length. Dimensions. V6. So V6 we have 0.5 meter. L7 we have 0.4 meter. So now we will trim the circle. So our geometry is ready. We'll make it extrude. So geometry is ready. We'll go here, update. Now we'll create mesh. So for mesh the interface has opened. generate mesh. It so very coarse mesh has generated. So as we are considering our geometry is 2D, so there should not be any element in between this, so we have to make conditions for it. So we'll insert sizing, take edges, so we'll select each edge type element size, number of division will take number of division 1, soft. So we have make a constraint for edges for only a single element. So on each edge we have only one element at boundary only. We'll make our mesh more coarse, more fine. Sorry. Mechanical CFD element size 0.5. Let's take it. Update. So our mesh has generated for 100 mm element gap. So we'll do the element size based on, like we will take different element size to reach out the grid independent, to reach out till grid independent. So we'll see by simulating the things, and we'll keep updating the grids, and we'll see that our solution should converge for the after a particular grid. So our solution will not dependent on grid. So we'll see in simulation part.
Hello everyone, my name is Keshav Verma, and from now onwards I will be taking over the whole scenario. The mesh is generated in Ansys Workbench. Now we have to export this mesh into .msh fluent file. After that we will import that as msh file into our OpenFOAM software. So for exporting the file into msh software, we have to just click on the file and then export options, and in export option we have to select mesh. After that fluent input file, export. I am creating a folder for the whole video. CFD and in the mesh file, mesh save. Now we can see that in the folder created named CFD Simulation video, we have a .msh file. Now let me discuss the whole procedure for the simulation. First, we have to select the solver according to our preference. Selecting a solver means according to our physics of the problem we have to select a solver in OpenFOAM which suits the physics of the problem and the CFD. After that, there are several tutorial cases for the software, and we have to just select the tutorial case which is most near to our physics problem. After that, we have to just add our geometry file to that case, import and convert that geometry file .msh file into the OpenFOAM CPP files, and after that we have to just process our data and see the results. For that, let me go to the OpenFOAM software location, computer, OPT. In OPT I have OpenFOAM 10. We are using OpenFOAM 10. Tutorials, and in tutorials we are doing some incompressible stuff. So incompressible, IcoFoam, cavity. We are using this. We will be using this tutorial case. Okay. So I am copying this folder into the simulation video folder. Please note that we should not do all the simulation in the OpenFOAM main directory. It will cause a lot of trouble in the time next to that. Please don't do that. In cavity we just have to copy our mesh file. We have copied our mesh file in the cavity. Now open the terminal, and in terminal write the command fluent mesh to foam, and after that we have to just add our file mesh.msh. Enter. Now this command converts our .msh file into the file in the constant folder. Let me give you a brief idea of what this folder means. First, zero constant folder. Zero folder actually give us the initial condition and the boundary condition. Initially, the u velocities of the simulation and the p pressure of the simulation. The constant folder gives us the geometry files and physical properties just like new. After that, the system folder contains all the solver files, just like control dict contains the time steps, how many time steps we want, what will be the end time, what will be the writing format, etc. Next is these are schemes and solutions, FV schemes and solutions. After moving to the simulation part, there is one thing left in the mesh file, that is patch formation. Let me start with the patch formation. This front and back part, this will be the front and back part, as we will be using the 2D geometry in this in the OpenFOAM. Actually 2D geometry is a 3D is a 3D, but in Ansys software you just need a surface to do the 2D simulation, but in OpenFOAM you need a 3D case with no elements on the thickness side. Okay. So let me start with the creating patches. Geometry import model. Insert named selection. I'm selecting these two and name that these two parts as front and back. Front and back. This will be the inlet. This will be the inlet. This is outlet. These two are walls. Insert. I am taking two patches for the diamond walls and the rest of the walls because of the we want drag and lift coefficient near the on the diamond walls. To calculate that, we need separate patches for that. So selecting diamond wall patches. 1, 2, 2. Just press the control and select the faces. 3, 4, and 5. Insert name selection. Done. Okay, we have made the patches. We have now again export the file in .msh file. CFD simulation video. This is simulation video cavity. I am replacing this. I am directly replacing this file. Yes. Okay. Now we are with the new mesh file. Again, I am converting this into the. Again, I am converting this mesh file into OpenFOAM mesh file. I'm done with the mesh formation. Now I can check the mesh using check mesh. We can see that the number of elements in the cell is 15,187, and the skewness of the geometry is 0.7, which is good. Now we can proceed with the boundary condition, applying boundary condition and changes in the patches. Now starting with the patches, after doing this mesh file conversion, we have created a folder named polymesh. In polymesh there are several things for defining the mesh. Our work is with the boundary folder. In boundary folder we just have the patches which we have defined in the Ansys Workbench. The front, back, inlet, outlet, empty, diamond. As we don't want to solve on front back sides, so mark it as empty. Inlet patch, outlet would be patch, walls are walls, diamond is walls. Okay, now we are with the geometry file. Now we have to construct our pressure and U file, applying boundary condition and initial conditions to that. Yes, so we have less patches here. We have to make patches. Wall inlet, inlet, outlet, inlet, wall, inlet, outlet, diamond. Yes, at inlet we need a fixed value, so we need this boundary condition at inlet, and at walls we need no slip condition, so we need this boundary condition at walls. The diamonds are also walls, so there is no slip. Boundary front and back are empty, so they are type empty. And at outlet we need actually pressure, inlet, outlet, velocity. So I just have to see the command for that. Outlet we need pressure, inlet, outlet, velocity. Initial velocity is 0, and at field velocity we just set the 0 value. Uniform 0, uniform 0. Initially there would not be any velocity at outlet in our case. Yes, we are with the velocity, initial and boundary conditions. Now we will move to the pressure boundary conditions. Similarly, in the pressure, we just have to add files like wall type 0 gradient, wall type 0 gradient, fixed walls, inlet, outlet, outlet, and diamond. I just have to check the pressure boundary condition at inlet at outlet from my previous files. These are pressure, inlet, at outlet conditions at my in the previous files using the same boundary condition here. We are with the pressure file. This is pressure and velocity files are done. Now we have to move to the control dictionary file, which contains all the simulation details. Going to the control dictionary file. Now the start time is 0, the end time would be 40. I'm not changing the delta t, and the writing interval would be at 100. Yes, at every 0.5 second it would write me a folder. Now we will apply the solver command, IcoFoam, the IcoFoam, the solver, and press enter. We got an error, expected an bracket reading vector space. Okay, actually what happened is in the u velocity file initial conditions, we added velocity as a scalar, but it need a vector quantity. So gedit in the 0 folder u file, the u file at inlet, at outlet. Actually we have entered a scalar, we have to enter a vector which is in the brackets 0 space 0, control S. Yes, now again applying the command, we got another error, which is the home Keshav Verma CFD Simulation video cavity 0 wall from line 24 to line. Okay, patch type empty and patch type no slip. Let me check the 0 boundary file and my boundary file, boundary condition files in constant folder. So gedit in 0 u file, and on the same time I want to check my constant boundary files, constant polymesh, and then boundary. Let me check this file, u file, wall, inlet, diamond, and front back. It seems good to me. And here it is again okay. There's an error that here the front and back are A is capital and B is capital, but here the A and B are small. I am replacing it with capital A and capital B. Now again using the command, yes, simulation works good. It will take a little time. Let me decrease the delta t, the time steps. So for that we have just to go to the system directory and control it. The solution will converge earlier. You can see that the files are generating for different times: 0.5, 1.1.5, 5, 10, 15, 20, 25, 30, 35, and so on. I am done with the simulation. You can see that we have reached 40 seconds. Now for checking this simulation, Parafoam, this is a command for visualizing the flows. In the OpenFOAM only solves the equation and give us the values at different time steps, and the Paraview software integrate these values into a visual so that we can see and visualize all the stuff. Apply. This is my boundary. This is my boundary field. View. Okay. Actually there is a error in axis. We have to give velocity in y-axis. We have give it to the x-axis, so we have to change the inlet velocity to y-axis. So go to the 0 folder, U, and just change the velocity to 1 in y-axis and 0 to the x-axis. Delete these files, and I need some more time steps, so 0.02 is a good number. Pressing this, and again starting my simulation, processing, IcoFoam. The time steps are generating here. In the meantime, we can actually in the lift and the drag coefficient of the whole scenario. For for calculating the lift and drag coefficient, I am showing you my previous simulations. For example, for finding the lift and drag coefficient, I have added some function in the control dictionary file in the system folder. For example, in this control dictionary file, I have added a function of forces which calculate the overall forces on the diamond, and the force coefficients, the drag and lift force coefficients on the diamond patch. The reason we have separate the walls and diamond patch. And this due to this the system calculated the post processing in this post processing folder. This post processing folder is generated, and in this post processing folder you can see a lot of force coefficient. For example, in this data you can find a lot of coefficient, drag coefficient, lift coefficient, water shedding factor, frequency, etc. And using all these we have written Python scripts to calculate and plot directly from these data. For example, if I want to plot my frequencies with respect to time, I just have to run this Python file python and python plots.py and enter. It will give me a drag coefficient and lift coefficient with time, and which is very good thing for as an engineers. And to check actually the relation with the Reynolds number, variation with the Reynolds number, we have made another scripts like plots. This actually calculate We calculate the average of a drag coefficient over the time for a particular Reynolds number and give us the graphs, plots, so that we can analyze data and give our conclusions. For example, if I run this plot .py file outside the actually in my Reynolds number effect folder, python plots.py, and enter, it sort of giving us error due to the file loss and etc. So what we can do, I can show you the results. For example, this is a Reynolds number versus mean lift coefficient, which is actually the relation of mean lift with respect to the Reynolds number. And similarly we can find the lift coefficient comparison and drag coefficient comparison. I have also had drag coefficient comparison, in which drag is increasing with increasing in Reynolds number. Similarly we can find the Strouhal number comparison. This is Strouhal number comparison. This all of this also, I can give you the exposure to the Paraview, the post-processing software for OpenFOAM. For that, let me take a case of a simulation that is already run. Now let me apply the parafoam command. Parafoam, yes, just apply, and what you can see is we make the background gray for better perspective. Yes, this is our domain, and we can see that I can show the U variations with the domain, with the time scaling. You can see simulation is going, actually giving us the animation of the overall thing, how the vortex recirculation regions are forming and how the vortex threading happens. Yes, also what we can do, let me open another file and do the open the parafoam on this file. Yes, what more we can do, we can find the overall average of a thing with the time of the whole domain as well as at any location in the domain. For example, if I want to plot the velocity average with respect to time, the overall domain velocity average with respect to time, I just have to plot over the time function and apply. I have to just apply these filters and it works so good. It will take a little bit of time and give a good results. Yes, we can see that average magnitude becomes 1, near to 1 at nearly 2.5 seconds, and we can see, we can give our conclusion using these simulation graphs and plots. And next thing I want to show you that we can give the probe location, that is a point where we want to calculate the average values over the time or anything else, integrated value over the time. Just apply the probe, give probe a location. I want to give 550.5 and it give this point, just star point, and just apply. We can find the value of 000 at 0. Yes, it will be 0 because we have set our initial condition as 0 in the domain. I just want to calculate the time plots of this velocity at this location. I just have to plot data over the time. Just click the control and space and this search tab open. Just click we have to search the plot over the time, select enter and choose apply. Now it will take a little bit of time and give us a oscillating plot just like this. The magnitude, magnitude increasing suddenly and then decrease and give us oscillating curve till 40 second, and it almost reaches a steady state at 40 second. and it is a good thing that we can analyze these stuffs. Next thing is that we can uh, we can make vector plots of velocity using this Paraview software known as glyphs you can see here, or you can choose from filters, data analysis, and from here you can see glyphs. Okay, just click on the glyphs. Click on the glyphs. Now glyph type arrow है, ओरिएंटेशन एरे हमारा U, ओके, स्केल एरे हमारा U, our scale array is U and orientation array is also U. We just have to say apply to this, and we can see this thing because at 0 time this is the velocity. If I make it 80 seconds, this is the velocity. Okay, I am changing the color to velocity, and this is now giving me the good results. These are a lot of vector, I don't want so many, so I make it 700. From 5000 I make it 700 and just apply. This is my domain actually, making more relatable, making colors. Okay, that's all, and after that we can also make streamlines using this software. What we can do, there is a stream tracer function, control and space, type stream tracer, yes, enter, and our line is through the diagonal of this cuboid, what we want on the surface of this cuboid. So I just have to change some coordinates. As our domain is of 5 mm thickness, I just have to change this thickness to 0.5, and this is on the surface. Say apply. Yes, these are the streamlines. These are dense, so we can make it more coarser by scaling down resolution, making the resolution to 100, 10 times lesser. You see the good results. These are the streamlines of the simulation. Okay, now the next thing I want to discuss is that the results of the simulation, about the grid independence and all that stuff. So I'm showing you some presentation, and through presentation I will be explaining this. First is animation. I have shown you the animation already in the video. Next is grid independence test and final mesh size. This is the grid independence plot, where I plot the average velocity into means these velocities are into 10 raised to power minus 5 and number of grid elements here, and we got that the number of elements become independent of the velocity at near 28,942 elements. We made a lot of grids, a lot of meshes for different sizes, 6 to 7 meshes, and simulating them and calculating average for at a particular location for the whole time. We got to know that at 28942 elements our mesh size become constant, so we can select the grid size 28942 elements. Next is streamline at 40 seconds. Streamline at 40 seconds, I have also shown how to plots, how can we draw the streamlines in the Paraview software. Next is vector plots, how to make vector plots in the software and how can we make this. Next is effect of Reynolds number on the coefficient of lift. The coefficient of lift actually makes a peak near the 2 into 10 raised to power 6 Reynolds number, and give then a decline to 3. So we can conclude that there is a peak in the lift when Reynolds number is increasing from 0.8 to 3 into 10 raised to power 6. Next is mean drag coefficient. The mean drag coefficient increases as we increase the Reynolds number. It is more or less the linear graph, or more or less near linear graph. And next is the Strouhal number. Strouhal number is precisely a linear graph, and as its frequency is falling on this line. Actually, we have calculated Strouhal number for 3 points, 0.8, 1.9, and nearby 3, and we got this graph. Next is a Reynolds number comparison on the velocity profile. We can see that at the low velocity profile, the Reynolds number make the flow laminar, and thus there are no vortex formation in the domain, thus no oscillations. As we increase the Reynolds number, the flow transition from laminar to turbulent, and thus our flow become more unsteady, unpredictable, and disordered. With this, I want to conclude this whole video, and thank you for being there.